round of applause, please.
Thanks. Yeah, I'm Ethan. I'm a PhD student at the University of Washington, and this is work with Harsha, who just graduated from UW and is now at UCSD. Vijay's at University of Minnesota, and then Arvind and Tom are my advisors at UW. So Traceroute's the most widely used internet diagnostic tool. You can use it to check if a destination's reachable. If it is, you can see what the route taken was. If it's not, you can try to figure out where the route's broken. You can check if the path's longer than necessary, so maybe there's some path inflation due to some out-of-date local pref, something like that going on. At University of Washington, we use Traceroute to map the internet. We have a system for predicting performance. We compare ISPs. A couple years ago, I was at NANOG when it was in Bellevue, and I talked about a preliminary version of my system called Hubble, which detects black holes and reachability problems. So, you know, if we're going to consider what it means for me to be able to reach some web server, there's this path from me to the web server. That's the yellow path shown there. And then there's also the path back. And Traceroute's a great tool to measure the path from you, the yellow one, but, you know, it doesn't really give you the path back. And what I quickly realized working on Hubble is if the problem's on the forward path, then we can get a pretty good idea of what's going on. But if it's on the reverse path, then we're pretty much flying blind. I'm only getting part of the story, and that's really been limiting my work. Similarly, you might want to understand the paths of the traffic that's coming back to you. So we were talking to people at a major website, and they had clients in a set of prefixes in Taiwan who were experiencing latencies of more than 500 milliseconds. And that was even though they were being redirected to a data center that was nearby in Southeast Asia. So the people from the website suspected that the problem was sort of an indirect reverse path, but they have almost no visibility into the reverse path. They need a way to measure the paths from their clients back to their network so that they can diagnose and address these performance problems. And then at Richard's Traceroute tutorial on Sunday, he said that asymmetric paths are the #1 plague of traceroutes, and similarly that the reverse path itself is almost invisible. So, you know, reverse path information is really useful for most of the same reasons as Traceroute, but if you want to get the reverse path from D, you have to actually run Traceroute on D. So one solution that we have is we can use public Traceroute servers. That's great, but there's only a few hundred of them, so if there's not one in the destination that you care about, you're sort of out of luck. You can maybe mail the mailing list, ask someone for help, maybe someone can issue a Traceroute for you. And often we have to fall back on assuming that there's symmetric routing, which is basically never true. So none of these really work as well or as often as you'd want, and we're basically using them because we have to, not because we want to. So the goal of this work is a reverse traceroute that can work without control of the destination. So we need a way to identify hops on the reverse path. We can't just use TTL limiting like Traceroute because the destination is going to set the TTL to a normal value. And anyway, even if there were TTL expirations along the path, those errors would go back to the destination instead of coming to us. So unlike TTL, IP options are reflected in the reply. So if you set an IP option on the forward probe, then it's going to be reflected in the reverse and you can get reverse path information. So we're going to use 2 IP options. The first one we're going to use is record route. Record route is going to record the first 9 routers along the path. So this is great. If the destination was within 8 hops, reverse hops will fill out the rest of those slots. But the average path on the internet is about 15 hops in each direction. So this is really only going to work if we care about a destination that's close to us. The second option that we're going to use is the timestamp option. With the timestamp option, you can specify up to 4 IP addresses, and each of them is going to record a timestamp if they're traversed in order. So the key there is that the timestamp checks for the routers in order. So a router's only going to stamp if its address is in the next open slot. This means that if we ping the destination D and ask for timestamps from D and then from R, D will timestamp when the probe gets there, and then R is only going to fill it out if it's on the reverse path after D is stamped. So we can use this to check if hops are on the reverse path. What we do is we can guess a reverse hop by using an internet map, and there's a number of mapping services available out there, and then we can check between the various adjacencies which one is actually the one. But unfortunately, the timestamp option has even less deployment than record route. It's filtered, and so in a couple slides I'm going to get to how often we see them supported. So we now have a couple techniques that can get us some reverse path information. But as I said, record route is only going to work if we happen to be near the destination. So what we're going to do is use distributed vantage points and source spoofing to help us get closer to more destinations. So in this case, we have my computer we have the web server. I'm trying to get the reverse path from the web server back to me, and then I have another computer down at the bottom that I can also use. And let's say that that other computer happens to be within 8 hops of the destination. What I can do is send a probe from that other computer, but spoof and say that it's coming from my computer. And so the response is going to come back to me, and so I'll get that reverse path information. So spoofing is going to let us simulate being in prefixes where we actually lack a presence. And I'll get more into spoofing in a second, but the key here is that a small number of well-distributed sources can support the entire system. And in the results that I'm going to present in this talk, I'm using 30 around the world to support the entire system. So, all right, I just said we're going to use spoofing, probably raise some flags. So we're definitely aware of the security issues, but we think that it's feasible to employ it safely as a useful tool with limits on it that are going to keep it from being dangerous. We only use a really restricted version of spoofing that's perfectly safe. We only ever spoof as nodes that we control. So essentially we're using it like a reply to address, telling the destination to reply to a different one of our nodes. We're sending it from one vantage point to another, but we're sort of bouncing it through the destination in the middle. So we envision a restricted version of spoofing that's available on measurement deployments with a list of who you're allowed to spoof as, rate limits set on how often you can do this, and also a restriction on destinations. And so far, we've sent millions of spoofed probes to tens of thousands of IP addresses, and we haven't received any complaints. So between the rate limiting that we're doing and also the fact that we only spoof as other nodes we control, this really has little in common with the sort of evil uses of spoofing where you're doing it to conceal who's doing the action. It's much more like the address rewriting that happens at NATS when you're writing in the address of another one of your nodes in order to control the flow of traffic to a cooperative host. So like I said before, all we need is a small number of spoofing vantage points to run the system, and spoofing can be filtered everywhere else as long as we can get it through on a couple ports from those couple vantage points. And this is going to let us approximate having control of the destinations where we lack a point of presence. We're basically doing one-hop loose source routing through the destinations. So options are generally sent to the route processor, so lots of networks filter them or ignore them to reduce the burden or the potential of abuse. So we want to look at, can we actually get the coverage with record route and timestamp that we need in order to build a system based on them? So what we did was we used Planet Lab, which is a measurement testbed with a couple hundred vantage points around the world. We issued trace routes from Planet Lab to essentially every routable prefix, and we took all the IP addresses that we saw in those trace routes. In terms of record route support, 58% of those IP addresses are within 8 hops of some Planet Lab vantage point. So that means 58% of them are close enough that we can send a record route from some Planet Lab vantage point and get some reverse hops. And then Rob Sherwood did some related work that he presented at SIGCOMM last year and found that about 1% of the IP addresses that are within, in his case, 9 hops of Planet Lab drop record route packets. About 9% of routers don't record, and then also about 13% of routers record if you encounter them not as part of an MPLS tunnel, but then don't record when you encounter them in a tunnel. So seems like pretty good coverage for record route. In terms of timestamp, of all those IP addresses that we saw, about 37% gave valid timestamps. An additional 18% replied but didn't set the timestamp. We zeroed in on the top 100 ASs in terms of the number of distinct IP addresses that we saw, and 61 of them supported timestamping from most routers. Only 5 of the top 100 supported it from less than 10% of the tested routers. So it seems like most of the big ASs are giving at least some support for these options. And then, you know, the ones where we don't see support, the options are either dropped, the option might be ignored, or it might be filtered along the path. So overall, there's pretty good support, but it's not universal. However, if we combine both these types of options with spoofing, we can get pretty good coverage, and you'll see the results on that shortly. So we now have a way to measure a reverse hop or maybe a couple reverse hops back from a destination. We need a way to turn that into a path. And what we're going to do is exploit destination-based routing. So most routing on the internet is destination-based. And so that means that the next hop depends only on the destination. It doesn't depend on the source or on the path that we've taken so far. This means that once we know the path from D to some router R, we need to only determine the path from R the rest of the way back to our source. We can ignore the first part of the path. Using this, we can stitch together the path incrementally. And this is a simplification with some exceptions, but it works often enough that we can build a system around it. So I've given an idea of the different techniques we use to build a path. Now I'm going to walk through an example just to illustrate how they fit together. So in this case, we have a source S, a destination D. We want the reverse path from D back to S. We have some vantage points V1, V2, V3 distributed around the world, and some of them are able to source spoof. The first thing that we're going to do is issue trace routes from each of our vantage points back to our source. This is going to give us an atlas of paths to the source, and if we intersect one of these paths, we're going to assume that the rest of the path that we care about is the same as it was along those blue lines, so we're just going to follow the blue line in. Next, we're going to find a vantage point that's within 8 hops of D. That means that it can send a record route and get some reverse path information. So in this case, let's say that V3 is within 8 hops of D. So V3 is going to send a ping to D with record route enabled, but it's going to spoof and claim that the ping came from S. D is going to get it. In this case, let's say when D receives it, 7 of the record route slots are filled out. D will add itself into the record route and then reply to S. And when S gets that response, we can see that there's now some reverse path information in it. We know that R1 is along the reverse path. So the reverse path looks like this. Now we're going to continue that process and find a vantage point that's within 8 hops of R1. In this case, let's say that V2 is within 8 hops. So V2 will send a record route ping, spoof as S. And let's say in this case, when it gets back to S, we've learned 2 more reverse hops, R2 and R3. So we know the reverse path looks like this. Now let's assume that none of our vantage points are within 8 hops of R3. What we do then is consider a topology map showing router connectivity, and we're going to look at the set of routers that are adjacent to R3. So let's say that R4 and R5 are adjacent to R3. We're going to use the timestamp option to check which of them is on the reverse path. So S is going to first check for R4, and it does that by sending a ping with timestamp enabled to R3, and it's going to ask for R3's timestamp and R4's timestamp. It's going to get to R3. R3 will fill out its timestamp and then reply back. And if R4 is on the reverse path, then when S receives the response, it should have R4's timestamp in it. We can check that. And when it gets back, R4 has timestamped. We now know that R4 is on the reverse path. And now we've intersected one of our known paths. So we're going to use destination-based routing to assume that it's going to follow the rest of the path in from V1. And so our reverse path looks like this. So we're able to combine together these techniques to get the complete path. And we're also working on an extension using some of these techniques to measure one-way link latency instead of just giving the standard round-trip time that you normally get with Traceroute. So I've shown you how it works. The next key question, I guess, is how often does it work? And so we did a study using about 30 Planet Lab sites as our spoofed record route sources, measured reverse paths from 200 random destinations around the internet back to 11 Planet Lab sites around the world. If we're not able to get a complete reverse path, what we can do is issue a forward trace route from the source to the destination, and we can assume that the last hop on it is symmetric and then try to get a reverse path back from there. If that doesn't work, we can assume the last 2 hops are symmetric, try again. If the destination is an end host, it's likely those last hops are symmetric or at least close to it, so hopefully this assumption won't hurt us too much. The metric that's captured in this graph is how many of the hops do we have to assume are symmetric in order to get a complete reverse path back the rest of the way. So it's a CDF, so the way you read it, along the x-axis we have the number of hops that we have to assume are symmetric back from the destination. On the y-axis, it's the cumulative distribution of source-destination pairs. So probably the best way is just to point out the points that I have marked there. In 40% of the cases, the value is 0, which means that we get a complete path back from the destination without assuming any symmetry. And then in the median case, we have to assume that the first hop back from the destination is symmetric, and then we can measure the rest of the path using our techniques. So it seems like we're often able to determine the complete path. When we can't, we can usually get it from a couple hops away. And the main limitation here is, I guess, the number of spoofing vantage points that we have, and then also networks that don't honor the options that we're sending. Beyond just giving you a path, we would like to give you the right path, or a path that looks similar to what you get if you could actually run Traceroute from the destination. So we did a study to evaluate that. In this case, we used 200 Planet Lab destinations, because in that case we can issue a Traceroute in both directions and compare the Traceroute from the destination to the reverse Traceroute that we measure from the source. And again, I'm using 11 Planet Lab sources. So the graph here shows the fraction the fraction of hops that you see on that directly measured traceroute that we also find on our reverse traceroute. And it's a CCDF. So to point out a couple points, the black line there is how well you do if you just assume that the path is symmetric. So in the median case there, we see that you'll get 38% of the hops right. So not too great. Our technique's the red line. In the median case, we can give you 87% of the same routers that you would see with Traceroute. So we're doing quite well identifying most of the hops. A big challenge, though, is identifying, it's hard to know if two hops are the same. And that's because Traceroute will generally give you the incoming interface on each router. Record route will often give you the outgoing one or sometimes the loopback. And so it's hard to know which of these IP addresses actually belong to the same router. We have some techniques that we've borrowed for alias identification, identifying which ones belong in the same router, but they don't always work. And so some of that gap, some of the reason we only identify 87% in the median case might just be because we don't know that the hops are the same. So to look at that a little bit, instead of considering if we get the routers right, we just looked at whether we get the POPs right, where by POP we just mean a given AS in a given city. And we basically identify POPs using DNS names. So in this case, the blue line shows that in the median, we get 100% of the same hops that you would see if you could issue traceroute from the destination back to your source. There are other reasons that we might return a slightly different path than you see with traceroute. For instance, we might get load balanced a different way, or there might be a path change in between the two measurements. So we issued traceroutes one day, then we issued traceroutes again the next day, which was about the time scale that I was issuing the reverse traceroutes on. We saw about 26% of these paths change day to day, either due to load balancing or actual path changes. So between those two stats, it seems like we miss a few hops sometimes, but it's largely due to alias issues and load balancing. And this is even in those cases where you have to assume the first hop or two are symmetric. Another issue is hidden routers. Some routers show up in record route but not trace route. Other routers show up in trace route but not record route. There's also instances where a destination-based assumption might break. For instance, if we hit a tunnel in the middle, it might not hold. And then perhaps, I don't know of any cases where options are routed differently, but there might be instances of that you guys can tell me about. It seems like we're doing pretty well. We can basically give you the same path that traceroute gives you. So now I've shown you that our system works pretty well, and I'm going to walk through an example of something that you might use it for. So in this case, we looked at latencies from Planet Lab sources to those 200 random destinations and looked for ones that were inflated based on the geographic location. So in this case, we measured 150 millisecond round trip time from Orlando to Seattle. So that's about double what you'd expect. And one case when you might be looking for instances like this is if you're a content provider, you might detect poor performance to a client. You want to try to debug that. So with current practices, what you could do is issue a traceroute. You could check if it's indirect. So that's what we did. Here's the traceroute. It starts in Florida, goes up to DC, comes back down to Florida, and then goes across to Seattle. So there is this detour up through DC, and that's costing us about 50 milliseconds. But it doesn't explain that big jump in round trip time between hops 9 and 10 from 53 milliseconds to 149 milliseconds. And so if you just had traceroute, at this point you'd be sort of stuck. You would suspect that there's some problem on the reverse path, but you don't really know what it is. If you look up at hop 5, you can also see that there's an inflated round trip time of 116 milliseconds. But that's not carrying through, so that's not affecting our RTT from Seattle. So with our tool, you can issue a reverse traceroute, and then you can check that reverse path to see if it's indirect. So that's what we did. And you see that the reverse path starts in Seattle, goes down to LA, and then comes back to Seattle, and then continues across the country through Chicago. So there's this big detour through LA, and that indirection is causing the inflated round trip time that we saw in the forward traceroute. So it seems like it's traveling down to LA on internet, then it's crossing over to transit rail, coming back to Seattle, and then going across the country. So this isn't necessarily a problem. For instance, that might be the only place that they peer. But we verified with a traceroute from UW that actually they do peer in Seattle. So there's not an obvious reason for this indirection. It could be some out-of-date information, or there could be a reason that it's happening on purpose. But our tool gives you a way to identify these problems and help troubleshoot these inflated delays that you're seeing. So to wrap up, Traceroute is obviously a very useful tool, but it doesn't provide you with the reverse path information. Our reverse traceroute provides complementary information and fixes this limitation with traceroute. It could give you much more complete picture during unreachability. I didn't really get into that, but we have some ideas on that, and actually they're going to be in the slides that are posted online if you want to take a look at them after. And generally, we're giving you most hops as if you issued a traceroute from the reverse site. There might be some dead zones due to options coverage. But we think that it's a useful enough tool to encourage supportive options. So in terms of how this affects you guys, we're hoping to have a downloadable tool by the RIPE meeting in May that you can run, and it will let you plug into our distributed system and get reverse paths back to you using our vantage points. You can email me, ethan@cs.washington.edu, if you'd like to be involved in that. The coverage is tied to the distribution of spoofing vantage points, and we're hoping to get people in the community to host some of these to increase our coverage. So it's similar to hosting a public traceroute server, except that our system will be the only thing accessing it. We're developing software for that right now, and the code's going to ensure safe rate limiting, spoofing safety, that we're only spoofing as nodes we control, and it's going to have admission control because it's all going to be going through our system. So if you have some hosts that you'd like to contribute, we'd love to have them. And with that, I'd like to conclude, and I'm happy to take questions.
So I think you covered this, but just to make it more explicit,
yeah.
How much of the source spoofing is Planet Lab lets you do that, and how much of that is actually plausibly on a lot of public networks?
So the MIT Spoofer project is estimating that about 20% of IP addresses can spoof probes. There was a discussion on NANOG a while ago, actually prompted by a preliminary talk that I did in this, where a number of people thought that the number was actually a lot higher than that. I think also that we only need a few set sites that are spoofing, and they only need to spoof over a set number of ports, so it's also something that could potentially be allowed to encourage the system because reverse path information is useful enough that providing a service based on this could be encouraged.
So on the one hand, this audience could break that functionality, but they could perhaps facilitate it working even more reliably.
Yeah, I think that if people decide that they want access to this information, this is a way to get it. And I mean, like I said, we only need a small number, so it also doesn't have to be like, okay, all of a sudden we turn off filtering. We have almost enough vantage points to get pretty good coverage already. So
that's great. Thank you.
Daryl Newcomb, Scenic. Had a chance, we, excuse me, we're all familiar with Traceroute in the ways that in interpreting its results. And I think with the methodology here, there's all kinds of interesting, probably real edge case kinds of,
sure.
Where like if there's because you're attempting to give an address in a packet to get a response back from an intermediary node, if that address appears multiple places, or people have as V4 exhaustion, people get creative with interface addressing, and routers respond with different things. These probes then in turn might be putting packets in, and then the results are that the tool gives is going to be potentially very, very strange. But I don't think that that's today. But
yeah, so there's certainly issues with that, and I think that I guess the best thing that we can do is continue the sort of comparison between traceroute and reverse traceroute in situations where we control it. So I could do a follow-up study using traceroute servers, something like that, and try to identify corner cases where we can actually identify the case based on the probe results. So things like tunnels, things like that, we might be able to actually identify that something weird going on and at least flag the results in those cases.
Great.
Anton Capella, 5nines Data. It strikes me that the reason we're going to want to use a tool like this is typically to debug problems in reachability or suspected, I don't know, maybe highly congested, highly multiplexed links from content, right? We're motivated to figure out what's wrong, right?
Right.
Something's clearly wrong. Could we change the last question you're asking, have some hosts can we use to have some applications we could stuff into this? Perhaps is there a way for you guys to extend the probe techniques, maybe add some packet trains or packet pairs to do things like dumbbell detection in this, so that in the reverse path, we're able to see not only, hey, here's how they reach us, and they're dumping through Cogent, but through UVNet or someone looks
right.
really well peered out, but maybe they are congested or aren't congested is a question we could perhaps seek to answer if this deployed infrastructure could support maybe one more probe type.
I think that that's really interesting, and it's the type of thing that we have on the to think about list, but we haven't done much with, and it's great to hear that you think that's an interesting thing to look at. The only thing that we've thought about is how these ideas can apply in situations of reachability problems where you can't even reach the destination, and we have some thoughts on that. But yeah, definitely these are good things to look at.
Let it be a voice for more encouragement.
Thanks.
Hi, Dave Temkin, Netflix. Have you guys thought about what could potentially happen in the case? This actually goes back to a discussion we had yesterday where an ISP might route traffic differently depending on the source of the traffic. So if it came in from peer versus transit and you're doing the spoofing, they might change that path depending on where that traffic came from.
Yeah, so I mean, certainly these cases where destination-based routing breaks some of the techniques that we're using. I guess, I mean, it's something we'd have to look into more. There might be ways, there are ways, we can use multiple vantage points to identify if you're getting different results from different places, and we might be able to do something intelligent about choosing the proper one to use in different cases.
That's kind of my question is, have you thought about a way of putting data together from multiple spots at one point to kind of figure out, hey, is this actually accurate?
So we do that to identify when there are multiple paths, either if it's load balancing or something like that, but we haven't looked that much into how to characterize what the cause of that is. So we're mostly at this point just assuming that it's hash-based load balancing, that it's not based on where things are coming from.
Okay.
But it's an interesting idea to look at, definitely. Thanks.